Yeah.
All right. I'm Eli Weinstock-Kerman. I'm actually one of the Sprigley folks that are here tonight, and I'm an engineering manager. I don't know if anyone wants to have a background. Maybe just keep going. I'm Jules Thomas.
Esther Lumsden.
Yeah, I'm Mark Mazik.
Are y'all in
That's why
Speedway?
you look familiar.
No.
No, actually, all different places.
Where?
I'm independent. I was at a place called Max Point for a few years.
Oh, I used to work in that same building.
Oh, okay, cool.
Currently at Deutsche Bank.
Oh, a precision lender, yeah.
I'm an engineering manager for Chef,
Which is what?
configuration management tools.
Oh, okay.
We like to pick confusing names.
And that's the firm name?
Mm-hmm. Yep.
Okay.
I'm Jared. I'm actually a senior engineer here at Sprigley. I work remotely from Amarillo, Texas.
Very good.
I'm just in here.
You're in town.
My name is Pat Clark. I'm a student and a QA intern at Wolf Tech.
Okay. Which outfit?
Avalera. Oh, this is the University of Oregon. It's an online program.
Okay.
Do you want to introduce yourself?
I'm Fred Brooks. I'm retired.
All right.
When I got 84, I figured it was time to retire.
I'm Chris Speck. I work for iRobot, which is actually based in Boston. I work at my house here. We make the robot, if you've never heard of it.
I've got one.
All right. How do you like it?
I like it.
Good.
Good.
Well, great. Probably can't see me in the video, but I'm the organizer of Papers We Love, and I'm honored to have Dr. Brooks here. And we're going to discuss informally the No Silver Bullet paper that he wrote. And I believe it was written in 1986.
Yeah.
Yeah.
So
And
30 years old.
Yeah, it's a very influential paper, and just wanted to get some informal questions.
What other papers have y'all been critiquing?
So in Papers We Love, in particular, we've read actual quick check testing paper, which is kind of like it's like a property-based testing
Okay.
tool. And then we've also read a paper on API design. So, and then we had the first session that we had is just learning to read a white paper. So that was actually the first session we had in January. And the goal is to essentially just get together and discuss an academic paper, and sometimes implement some of the concepts if we can do that. Yeah, this is quite a treat to have you here. So I'd be really interested to get your thoughts on how some things have changed since you wrote that paper, which I'm sure is a lot.
Well, I think y'all are the better judges what have changed. But the paper comes in two parts. The first part should have survived, and that is, it should still be valid. And that, the central thesis is people were expecting and hoping that software would advance as fast as hardware. And it hasn't, and it hadn't by 1986, and I was speaking from 1964 viewpoint. And so the question was why? The first answer is the anomaly is not that software is slow, but that hardware is fast. Faster than any other technology in the history of the world. And the first supercomputer I worked on, fresh out of graduate school, was the Stretch, IBM Stretch. It was its first transistorized machine. It was the world's fastest machine from 1965 until 1968. We made 9 of them. We sold them for $10 million a piece, mostly to atomic energy commissions and weather bureaus of England, France, and the U.S. stood 5 feet high, 5 feet deep, 15 feet long. We built a plug-in card for the National Security Agency's copy only that added another 20 feet, and it did cryptographic character streaming. So, but it relied on the mainframe. This machine is faster, has a bigger memory, has more input-output devices, and costs $600. You can take that technology advance either in cost this way, or you can take it in performance, and you look at something like the Oak Ridge supercomputer, you know, rows and rows and rows and rows of cabinets. So the remarkable thing is that hardware is so fast, has moved so fast, and the basic reason is that it shifted from being an assembly operation where you had to put the transistors in holes in the plug board, in cards, to a process operation where you're making 1 million transistors a week and getting decent yields. So back to software. So then I tried to analyze what is it that makes software hard and slow. But I make an assertion. The assertion was that there isn't going to be, there is not and is not going to be a silver bullet that's going to solve the software problem. And I further assert that there won't ever be, and that's a strong assertion, but I made it concrete by saying there will not be in 10 years anything that gives an order of magnitude improvement in productivity, software productivity. Well, the 10 years came and went. But the immediate reaction was a whole set of papers that said, oh yes, there is a silver bullet, and here it is. There was not a single paper that said, oh yes, there is a silver bullet, and there it is. They were all about my version of a silver bullet. Now, I've found one I'm using, somebody else built it, and it's really great. None of those appeared, not one. Well, then I go into what are the reasons, and the first one is complexity, that we never, as a human beings, built anything that's got more different parts in it than a big operating system. We built some very complicated things, the International Space Station, but it doesn't have more parts in it than a big operating system. And of course, one reason is that if you start replicating the same parts, you write a subroutine. And another characteristic is that it has to conform to many, many external constraints. Application constraints, hardware constraints, available technology constraints, and therefore it is subject to being changeable because the constraints keep changing fast. One of some internships I had was working on a 40-state payroll for Marathon Oil Company. They were converting from a punch card system to an IBM 650. And doing a 40-state payroll on an IBM 650 with 2,000 words of memory was a trick. But with a 40-state payroll, you've got 40 state legislators changing the rules all the time, not counting feds. And so there's no such thing as build it and leave it be. And then the last characteristic that I think is inherent is that it's invisible. You can't draw a two-dimensional flow chart that fully describes the interconnectivity of a standard cell. Then in the second part of the paper, I say, well, what are some of the silver bullets people have put forth? And I describes some, then that section is ancient history and not worth detailing. And some say, and then the next section says, but things are not hopeless. There are ways to move forward, and here are some candidates, and here are the ones I like. And I bet my money then on object-oriented programming, and I think that was a good bet. So there's the synopsis real quickly. So, but the fundamental thesis is that because of those 4 basic properties, they're never going to be a magic solution. Okay. The silver bullet comes from the fact that I think werewolves were supposed to be killable only with silver bullet. So there.
That's great. Thank you for that synopsis. I had a couple of questions for you about the paper that I thought was pretty interesting. When you said, there's a part where you said an order of magnitude gain can be made by object-oriented programming only if the unnecessary underbrush of type specification remaining today in our programming language itself is itself responsible for 9/10 of the work involved in designing a program product. I doubt it. When you said the type specification, that's where I was wondering what you meant by that. You mean like types like in...
Data types.
Data types in program language?
I don't even know what I meant.
I was curious because like now with the rise of some functional programming languages and in particular I think that Ada was the language that you spoke of. Is there any other languages that you think that have been even more influential than Ada than when you
Well,
wrote
I
the
don't
paper?
think Ada was very influential. It was early, but I don't think. The ideas from Ada were influential, but a paper you ought to read is Parnas's original one on information hiding, which was what fundamentally defined what is the basis for object-oriented programming. And he said you want to construct modules that are closed so that what's inside cannot be seen, but only what can be seen is what goes in, what comes out. And the question of how it's implemented should be hidden completely. I thought he was wrong. I said so. Now I say in chapter 19 of the Mythical Man Month that I was wrong and he was right. In building OS 360, we were concerned, we made the mistake of having control blocks that everybody could see, and it provided all kinds of parameters, and everybody had used the same, accessed the same control blocks, and that had some advantages in standardization. But the fact that everybody could see them did not. And that was why I thought Parnas was wrong. But I think from a purely theoretical point of view and from a practical point of view, moving to the only way we're going to see orders of magnitude improvement is to move to orders of magnitude higher levels of abstraction, and that's what modularization does. We now deal with the module as an abstract entity, and we deal only with its visible properties, its specified properties. And you can change the data structures inside, and you can change the algorithms inside, and you can change all kinds of stuff inside it. Doesn't affect how it works. May affect how fast it works, may affect how much memory it takes, but it doesn't affect the function. And so that moves us up a level of abstraction. And the biggest jump we had seen in the history of software was that the first machine I learned to program was on IBM 701, which was its first scientific computer. This was in North American Aviation a summer internship when I was a college junior. It was before assembly programs. We programmed in octal absolute. It had 4,000 half words of memory, and I got myself a piece of roof ceiling tile that had 64 by 64 holes in it, and I got a box of matches, and I kept track of live variables by putting matches in holes, all right? There was no floating point. Some folks at United Aircraft wrote a floating point subroutine library, but I was doing data reduction from the rocket, and to do it fast, you had to do it in fixed point. And if you remember your elementary computer architecture, a fixed point divide requires the divisor to be larger in absolute value than the dividend, or else you would get a quotient overflow. And that meant that one had to know what the numbers were going to be and had to shift and shift and shift and shift. So you did the shifting, since it wasn't a floating point engine to do it for you. And this was the most common cause of bugs. Okay, you miss guess on it and get a floating divide. The 701 had a mean free error time of about 10 minutes. So you'd roll your program out the drum, you'd hold memory out the drum. Well, the memory wasn't that big, you could roll it out the drum in a few seconds, and then when the machine goofed, if you could figure out that it had goofed, because there was no checking of any kind, you rolled it back in and started, so you did, you know, this kind of thing. So assembly programs were a very big step forward. But the biggest one in productivity was Fortran. Fortran is the best measurements I've seen, made about a 5 times difference in productivity of writing versus assembly code. By analogy to that, I concluded then and conclude now that the only way we're going to see big gains in software productivity is by higher levels of abstraction. And that's why object-oriented programming seemed to me to be the most promising, because it moved us up a level of abstraction. Now, the one I bet on loudest in the paper is don't build it at all, buy it. That moves you up another level of abstraction. And of course, that's what's happened to things like payrolls. My dissertation advisor, Howard Aiken, was of the belief that we could really get substantial gains in hardware design by specializing the machines with the problem. And that is true in cryptography, but that's not true in many things. No, my assignment was to design a computing machine for doing payrolls. And to his disappointment, what I found was you could specialize to the class of serial processing, like tape to tape or disk to disk, utility billing that you run once a month, but you have a query capability, and okay. And specialize, and that was a large class. That was what had supported the punch card industry. So insurance premium accounting, utility billing, payroll, railroad car accounting, the things that had been automated from Hollerith with the census to start with in 1900 up to the punch card machines really in the 1910s, up to really Social Security on punch card machines, with these big serial data processing problems, which you constrained to do them by batch, and you sorted your transactions into file order, and you passed the file once, and you applied the transactions against them one at a time. Well, yeah, you could save money by designing a machine to do that class of problems, but any further specialization, you could put in a trick operation or two. And the most important one and the most useful one is a nonlinear function. So it turns out that these problems are full of calculations where you have steps. So if think of your income tax table, all right, is a good example. And so that's piecewise linear functions, and you can put in a single instruction that takes effect for piecewise. The ordinate and the abscissa where the steps occur, and bingo, you can evaluate such functions very fast. But, you know, that's not a big game. And so I still think that the gains are going to have to come from higher levels of abstraction, and that means using libraries skillfully, and we all do that. That was Unix's first big contribution. The tools for using library programs, pipes and filters. I don't know where the next one is, but I know what it's going to be like. It's going to be like an abstraction job.
So the 3 or 4 that you kind of outlined were assembly, Fortran, object-oriented programming, using libraries skillfully, build and buy versus build, and you kind of maybe libraries and then buy versus build. Maybe that's kind of a similar kind of thing. Are there any others historically that stand out to you?
No.
No, those are kind of the big 3 or the big 4.
Yeah, time sharing.
Time sharing.
Time sharing. As opposed to putting a program in and waiting for it to come back with the bug found. Bug not found, but some bug to be found.
Yep.
When I was at North American, we went down over in the eastern part of the valley. The computer was over at Inglewood at the airport. And so a station wagon went back and forth twice a day carrying cards. So now, turned out, as you well know, the thing that determines speed of debugging is number of turnarounds, not speed of machine. And so, you know, if you were lucky, you got 1 turnaround a day. If you were really lucky, you might get 2 turnarounds a day because the station wagon. But what those of us who did every now and then was get in the station wagon and go over to Inglewood, because the 701 was fast, and the card equipment was fast, and I think this. And the fact that it was directly attached distinguished it from the UNIVAC competitors, and I think made the commercials the difference in the success of the two. Because in the UNIVAC system, you had to go card to tape, then mount the tape, then run your code, then dismount the tape, then take it to a printer, mount it on the printer. And so the UNIVAC scientific machine, the 1103, 1105, were faster than the IBM competitors, but the designers had spent their money on the runtime after you debug, and not on the debugging process. And as we all know now, given real fast turnaround, it determines how long it takes to get your program to run. So directly attached terminals made a big jump, factor of 2, I would say.
How do you think about measuring developer productivity of programming language? I mean, on the hardware side, you have operations per second or whatever.
I don't know. Lines of code are obviously the easiest thing to do. We all understand that best programmers write the shortest programs. and the published results show that they do it quicker too. So you get lower productivity, but you get the job done sooner.
It's like if you have a common programming problem to benchmark, I don't know, techniques or languages against.
Well, that's why the people web book is so useful. Is the authors run a consulting operation for software firms in New York, and every year they would have war games. And the war games were kind of a week-long programming exercise. And if you were one of their clients, you could send as many teams as you wanted. Everybody tackled the same thing. You got back data on how your teams did relative to teams in general, but you didn't know how they did relative to any particular competitor's team. And what DeMarco and Lista got was data to correlate performance against other factors. And so Peopleware is a priceless book. I think it's one of the very best, and it's Peopleware 2, I think, now in the current edition. I don't think they've done a 3. And they're not running the data producing operation anymore, so they don't have a basis for really updating. And so they found out things like somehow the places that are more favorable places to work seem to have much higher productivity. And they go into various factors like furniture and light and so forth. And they say something which is very true, and that is, we don't really know whether that's because it makes the same people work better or whether it attracts better people, but it doesn't matter. Spend your money for the pluses and you'll get the benefit. So if you've never studied that book, you need to study that book. It's real. DeMarco has written very many other good books, including Slack.
Yes.
How many of you are familiar with the collected works of Parnas? David Parnas. You've never heard of David Parnas? I keep nominating him for a Turing Award. He was really the father of software. And
separate software construction into the essential and the inessential, or the accidental.
accidental. To quote Aristotle.
Right.
I got that from my wife.
Okay. The accidental part?
No, following Aristotle.
Oh, okay.
She's did a physics master's at Harvard, but she did a physics bachelor's at Rochester and an organ minor at Eastman at the same time. And then at Harvard she stayed an extra year and did an extra year of music. So after we started having children, she left the physics job at IBM when she was working on transistor circuits and became a professional music teacher, teaching kids violin, Suzuki method. And she wrote a paper on what are the essentials of the Suzuki method and what are the things that people just copy because Suzuki said they're not essential. So the paper was the essentials and accident of Suzuki methodology. So I thought that was a great idea. So I picked it up.
Nice.
And so that's the basis on which I cut it. And the basis for my argument that it's the way forward from 1986 was going to be slower than the way to 1986 was that the real improvements to that point, things like time sharing or Fortran or even assembly languages, we're tackling the accidental things that got in the way, and the essential things are the complexity. Hadn't tackled those, all right? And my thesis was, unless 90% of what remained was accidental, we could get rid of all the accidentals and it wasn't going to give a tenfold improvement. Okay. We had done a lot of house cleaning on that. We no longer were writing single lines of code and keeping track in our head of where we'd left variables and all that. So, and time sharing really cleaned out a whole lot of the remaining accidentals.
So when we
So
think
my argument is a mathematical one.
I guess I had a question off of that though, which was, do you have a gut feel for, when you wrote this article versus today or any time in between, what percentage of a programmer's work is accidental versus essential?
I haven't worked in software in 30 years,
All right.
so you know better than I.
It's all accidental.
I don't think so. I don't think so. Where did the bugs come from? They're usually conceptual.
Are you aware of any work that tackles, like a current work at least, that is attempt to tackle any of the four biggies?
I haven't followed the
All
literature.
right.
I'm really ignorant. I've been doing virtual reality.
But that seems to, if we say this is essential versus accidental, and the essential really is the conceptual model work, right? That seems to imply that your next jump may actually be in process or some kind of tooling in that space, in the rigor of how we approach conceptually software development, as opposed to
The effectiveness of how we approach conceptually, not necessarily the rigor. So, people do mathematical proofs of programs, but they don't do it unless it's the inner kernel of the critical security part of what you're doing, because it's so much work. And, as has been demonstrated in mathematics through the centuries, you get proofs from them too. There have been many proofs published that have later been found flaws. Well, so your proof about that your program is going to give the answer you expect is subject to the same flaws as any other mathematical proof. It radically improves the odds, but it doesn't make it foolproof. Now, you had another question?
Well,
I
I
interrupted you.
think of modern software development, right? And we've gone from define everything up front to like agile methodologies, Kanban, try and visualize the work you do. That doesn't necessarily drive down into exactly the program you're writing. But it seems like those potentially are avenues to tackle more of the essentials,
Yes.
complexity than say an improvement in
And I argue
program.
in the design of design. One of you got a copy of it here. There's a body of theory that starts with Herb Simon that said you got to get the requirements right before you start your design. And I argue that you can't. And so the whole first part of that book is essentially an argument among design theorists. So the standard German engineering book, been through 7 editions, Paul and Weitz, and they fiercely argue that you've got to get the requirements completely right. You can't.
I guess I see a lot of the agile stuff in the Kanban is trying to visualize, trying to sort of make more clear sort of the process of building the software, of kind of a high level, this, we're going to build this, and we're going to build feature X, Y, and Z into this product. But how feature X works,
Yeah.
I mean, I don't think we should like even go into a deep dive in each story and say that sort of thing. But I think it's the process part of it, but not the actual how does the software work kind of be.
Well, then, as a corollary, I think the paper dances around visual programming is a possibility, right? And yet, even today,
But it doesn't advocate it.
right? And well, it's an interesting thing, right? Even now, 30 years on, like every visual, like we don't use visual programming at all. All those tools have, for whatever reason, never caught on or failed in some way or another. And so then, I guess if the question is that visualization could potentially help so much, why do we hardly use any visualization at all?
I don't think it does. Because what we're dealing with isn't visualizable. It can't be represented in 3 dimensions. Just think of all the lines of connection you have, for example, among data types. Then you have your flow chart, sequencing. You connect in different spaces, as it were. When you want a runtime, if you're trying to do a performance analysis, you want to know the runtime behavior. You start with the static behavior. So I think you can visualize pieces usefully, but I don't think the notion that if we just had the right graphics tools, it would make a big difference. And as you say, people have kept on proposing them. They've mostly been academics.
So if you had to, if you were, you want to answer it?
No, I'm not going to answer it.
Would you like me to answer it? I can talk to the telemarketer for you. If you were a 24-year-old you today, going into either academia or professional practice, where would you put time and effort, or where would you put your money?
I would go at the intersection of computing and biology.
Biology?
I tell every every high school student I meet is asked that question.
So
I say I picked a perfect career for the last half of the 20th century.
So I was specifically going to ask about where would you put your money in terms of program productivity? If you were, I know you said you don't know what's next. You don't know what's next.
I haven't thought about that.
Hadn't thought about it.
I think there's still an aspect of biology, right? Because a big piece of it is trying to abstract more, so you don't necessarily have to think at quite the same level of detail. How we think, how we describe problems, a lot of things people are doing with AI, they're doing it in terms of trying to understand the human brain, and I think that it's also because we're trying to understand problems and we only have our own perspective to understand them from, so.
Most of the AI is not based on understanding the human brain. Because we don't understand the human brain. Over the years, I've collaborated with scientists on, I say a computer scientist is a toolsmith. We build things to help people do their jobs. And so for 30-some years, I collaborated with a pair of protein chemists at Duke, David J. Richardson. And the best way to make your computer science look good in a collaboration is find real bright collaborators. At one point, Jane was even mentioned for on the list of people were talking about for Nobel Prizes. So, I picked my collaborators well. And we were able to accomplish some very good things. The first protein that was ever solved without building a brass model was solved on a system my students built in our lab. Dave and Jane spent many a night because we got on the Mach 75 third shift time for them to run this stuff, and we needed all the performance we could get. And they went on to do, and their students went on to discover how this marvelous protein in fact works, how the electric fields it generates bring the ion into the little narrow trap, how the histidine flips back and forth and does a self-resetting mousetrap, turning superoxide either into water or to hydrogen peroxide or water or hydrogen peroxide. And then how once it's neutralized, it drifts out and makes room in the little funnel for the next one that could be drawn in by the electric fields where their students did that work. And we helped. All right, but looking over their shoulders, watching them do this fascinating work. And we've collaborated with physicists who in turn are collaborating. They do forces. And they've collaborated with people who are trying to figure out what is it that actually happens in cell mitosis. Where are the forces that pull it apart? What triggers those forces? What applies those forces? And they have a model. Okay, well, now the next question is how well does the model predict the measurements? And they worked with the blood clotting people and working on individual fibrin threads and measuring the forces required to break the thread using atomic force microscope. Okay, and we build the stuff that help them do the measurements and reduce the data and visualize it and so forth. And 2 members of our department now have joint appointments in genetics because the sequencing and the sequence matching and all that is a target for algorithms. Okay, really clever algorithms. And the biologists are only now getting the hang of what computing can do for them, whereas the physicists did it 50 years ago and the chemists came along later with molecular simulation and all that. But the biologists are only now getting to the point where young ones know they have to know computing. Okay. So I say the intellectual excitement of the next 50 years in science is going to be in biology. There's so much to be discovered, so much to be understood. Get on board. Free ride. Now, commercially, that's another question. I don't know what the $1 million app is going to be. There's no shortage of candidates.
Something I was picking up in your question was kind of a question if, maybe the things that we need are more cognitive tools or more conceptual tools for picking off layers of abstraction. Is that part of it? I mean, part of it kind of what you're getting at? Yeah.
Well, the other thing that's happening is big data. I mean, Google, when I was a graduate student, one of my peers was working on Russian to English translation. And all the years since, people have worked on being able to do language translation, and they make pitifully poor progress. And Google took an entirely different approach and said, well, let's swamp it with data. Swamp it with data. Don't try to be smart. Big progress. And that's happening in field after field. So learning those techniques and trying to figure out where and how they can be applied is going to be an area of great commercial promise on application after application. Computer security. How many ways can people invent to steal? That game's never going to end.
I was going to say, always one more than we're ready for. It's always going to be on the way.
I have a question for you about, in the paper, you speak a I guess the, say, computer naive professionals. So, and I think in relation to like spreadsheets, enabling them to do things where they don't have to write a program.
Yeah, where they don't know they're writing programs.
Right, right. What do you think of, like in England, I've heard that they're instituting like K through 12, teaching computer science as a core curriculum. Do you think that holds like a lot of promise for the future, like teaching young children computer science? What are your thoughts on that, Dr. Brooks?
Teaching them computing, yes. Teaching them computer science, no. And I put the transition in algorithms. So, kind of, this is the second year that our students really get into computer science when they do data structures and algorithms. Programming is not computer science. It's very useful. And yes, teaching them by means of starting with spreadsheets, great. You get quick results. And you can teach coding by the turtle techniques, where you just tell the turtle to turn left and right. You're teaching sequential algorithmic thinking, and you're providing fun and giving instant reward. I remember when my high school daughter first got her hands on an Apple II, for her project she programmed a key battle in the Russo-Japanese naval war on the Apple II screen, just using characters for the ships. Well, what fun, okay? And you could see how the battle went. That's a far cry from today's computer graphics. Did I really answer your question, or did I miss the heart?
Yeah, no, I think you answered it perfectly. Yeah, I was just curious because I know that was a point on the paper, and you know, because there's another thing that I was wanted to ask you. And when you talked about, I believe there's a part where you said Parnas, and I think that it was on artificial intelligence. What do you think of, like, for expert systems, like machine learning, like you know, what role that could have on expert systems? Do you have any like thoughts on that?
Well, if we go through the history of AI, there was a phase when expert systems were the promising component. And they got fancier. They started with rule-based systems, and people developed techniques for extracting the knowledge from the expert, which is the hard part, and for turning it into rules. The most successful such system was one Digital built for configuring Digital's own computer configurations for customers. It got up to about 2,400 rules. It was really started being quite successful at 600 rules. And it bogged down at 2,400 because it turned out that anytime you tried to make a new rule, determining whether it was consistent with all the previous ones was an exponential problem. And so what people have kind of come to the conclusion to is if you've got a problem that you can do really nicely with 600 rules, go to it. If not, that's probably not the way to go at it. So. And I'm a strong believer in spiral models. Go round and round, refine your requirements, refine your product, refine your testing, test at every level. mentioned that. And no silver bullet paper.
Yeah, page 199.
Yeah.
It's interesting there actually, because basically in those two paragraphs on page 199, which is about requirements, refinement, and rapid prototyping here in 1986, you sort of, this is agile. Like you define
Yeah.
agility. Therefore, the most important function that software builders do for their clients is the iterative extraction and refinement of product requirements. The truth is, you say, the clients do not know what they want. They usually don't even know what questions must be answered. And they've never, almost never have thought of the problem in the detail that must be specified. So, yeah, that's basically agile.
Yep.
Or rather, they, yeah.
What's that?
Well, I'm just saying, you coined it first. You should get a better name.
No, I didn't coin it, I described it.
Right,
The
right.
fellow who coined it did a better job. But Barry Bain is probably the outstanding scholar in the field of software engineering, and if you're not familiar with the book of his collected works, you ought to at least leaf your way through it too, because Barry, his software engineering economics was groundbreaking, and he was chief technology officer at TRW Systems. And as such, he had data from 172 software projects, if I recall, that were internal. And so he was able to do a whole lot with that data and modeling it. But he's gone on and worked on so many different areas in software, and he's so smart that I recommend you look at his collected works. Some of his students put them together. I forget.
What was the name?
Huh?
What was the name?
Boehm, Barry Bain.
Yeah, the People Work book quotes him extensively, I think, as well.
Yes,
a lot
sure.
of his data.
Well,
So how about kind of the last part of the essay? Or I guess it's, yeah, just towards the end, where you say great designers.
Yes.
So you talk about promising things, and one of them is this prototyping and rapid prototyping, evolution and growing software. The last thing you mentioned is these great designers, meaning people. And so you're talking about basically training people in how to be
raising them.
raising them.
Yeah. Well, one of the impressive things about working with IBM company is their whole process for growing managers. Starting, identifying them early, giving them good training, and going right on up to the point where they'll take turns with you promising them to be an aide-de-camp to the CEO. And kind of like David was for Saul, you know. It's interesting, this technique that's used throughout the scripture for training the great leaders. So somehow Moses got raised in the court of Egypt, somehow by this weird, strange process of throwing him in a basket on the river. He grew up a prince of Egypt, and so when it comes time to set up a law system for a whole people, he's seen law systems work. He's been trained in law systems. Somehow David, as the musician in the court, gets to watch cases being tried and decided, so that when he's king, he's been trained. St. Paul gets his PhD in theology from the best scholar of the time, Gamaliel. And then in each case, the person is broken. And so Moses is out in the wilderness looking after sheep, and David is running from Saul in the mountains, and St. Paul's off in the desert for 3 years. So they get trained and then get broken and then get used. And I think the whole seeing that you want to use the best available training. The thing that the IBM company did not have was any process for training technical people. The managers got rotated from one job to another so they get exposed. They had mentors look after them. They had people tracking their careers, okay? None of that was happening for the designers. Well, my argument is elaborated some more in the designer design book. It's at least as crucial to have them trained and identified and selected as it is to have your managers. So go do that.
So you end it with, space does not permit a lengthy discussion, but here are steps on how to grow great designers, and you list 4 or 5 steps. Where else can we look to find your thoughts? In this book?
I don't know, I would say that, at least in my experience, we still don't do a good job of training technical people, designers, developers, or anything else once we get them on board. I think a lot of companies rely on them doing it themselves.
Mm-hmm. I taught software engineering lab for 22 times. And I evolved to a pattern in which I strongly preferred 4-person teams. 3 usually end up with 2 versus 1 somewhere. And that's true with you youngins if you've got 3 children there. In our house we had 2 boys and a girl, and I've seen the drama of Knight, Maiden, and Dragon played out in 1,000 stages. The dragon picks on the maiden and the knight comes to her rescue. All right? The dragon being number 2 and the knight being number 1 and the maiden being number 3. Other households have different dramas, but they have standard dramas. And I think the process of finding and growing the leaders is of great importance. And so I insisted that even on 4-person teams that they pick separately a boss and a technical director. And I took this notion from the movies. You have a producer and a director. Whose movie is it? Who works for whom? The director works for the producer. Whose credits are last on the screen? The director. Because he's responsible for the artistic content. Okay, I think the same thing works in a software project. Somebody's got to keep you on schedule, get all the resources, deal with the customers, fend off the assaults. All right, that's the producer's job. Somebody should have a clean conceptual idea of the product and should spend all of its time making sure that what gets built fits the clean conceptual idea. And if a product is not, I once was invited as a consultant to look over a proposed new computer architecture. In the first hour, somebody came in and talked about the instruction sequencing, and in the next hour, somebody came in and talked about the data structures, and the next hour, somebody came in and talked about the arithmetic. And finally, I said, well, let me talk to the person who understands the whole thing. There isn't one. Oh, I knew this was the smell of death and that project would not succeed, and it did not. It collapsed at a great expense. But there was no one who understood it all. Well, if nobody on the building team understands it, how do you expect the users, the people who write the software, the operating system for it to understand it, if nobody understands how this machine works? So I'm a strong believer in having a technical director, and they have technical responsibility. So, but somebody else has got the function of making it happen, and the technical director determines what is to be made to happen. And I believe you can train people can train the same people for both of those roles. Although in many cases, the right talents are different for the two cases, so the producer's got to be a communicator. The requirements, I learned the hard way. That same summer I was at North American Aviation. As an intern, I was called to build a database system for this project engineer who was in charge of a radar subsystem on one airplane. And he had 10,000 drawings, and he wanted a database system that would keep track of the update status, when it was updated, who updated it. And so my job was to build him a database system. This was in the days before computer databases. And as I say, I was programming a 701. But I had been trained in punch card techniques, so I built him a punch card database system. Took him to report, showed what he wanted. Could you put them into goes into order, indent them up to 10 levels, so that the components of each subsystem would sort them in tree structure order, and show by indentation what the level is. Yeah, well, that wasn't the first thing he asked for. First he asked for an asterisk on the ones that were more than 3 months old, and then one thing and another, one thing and another. Then he got to the goes into order. That one was not an overnight job, but because you build it on the relays of the accounting machine, and got it built, took it to him. But this whole process of asking for something different happened every day for 2 weeks. I got madder and madder. And finally I realized that this was the useful thing I was doing for him, was making him think through what it was he wanted. And so then I quit being mad and started being useful. But I had, been delivering him what he wanted every day, and every day he wanted something else. So that convinced me.
So it feels like there's a parallel between time sharing, allowing you to have faster feedback, faster debugging, and just finding better ways to prototype and show people.
Quick prototypes.
Just put it in front of them more often and let them kind of see and think through the next step.
Graphics makes that so much easier. Harlan Miller said, build your inner loop first and have dummies for all the subroutines. And then put on the subroutines one by one and show them to your client. To keep refining what it is they want. So you start with a set of stubs. And if you need to fake what goes on the screen, put a prototype and show the client you fake it. Or you fix it so it works for the main case, but not for all the exceptions or whatever.
Just enough to get to the next unknown or the next.
You get the reaction from the person whose application, whose need is that.
Dr. Brooks, I have one last question for you. You mentioned about database systems, and in the paper, I think you mentioned like one area in particular, I think was integrated database systems, where you see that could be improved upon. So, I'm assuming at the paper you were talking about like some of the business logic that people had to maintain in their head is a difficult thing. Is there anything else you think that, like, with database systems in particular, like that could influence some of the accidental difficulties? Do you think that plays any role, or?
My peer colleague in graduate school, Jerry Salton, wrote the best single study of a business application that's ever been done for his dissertation. He studied the Boston Gas Company's billing process. And he studied it in infinite detail, and I think he found 230 exceptions to the mainline process for generating the gas bills and documented them. And you stop and think about it, no wonder they've got a software problem. Their policies have got all these exceptions. And what you would hope is that in the process of helping the customer get his application running, which they did, Jerry didn't, Jerry studied it, but that they would have somebody wise enough upstairs to say, we need to clean out the policies. All right. This happened to a degree in payrolls. Originally, everybody wrote custom payrolls to fit the policies, and then later they found they could buy a payroll package, but somehow it didn't cover all the exceptions. Well, how many of those do we need? Mm-hmm. And in many cases, some cleanup happened. Unfortunately, as far as I can tell, that hasn't happened in any of the federal systems. There hadn't been an upper level review of the whole system of the software plus the policies. So look at the income tax.
My previous company, just 6 months ago, we went through the policy documents for one of the national banks. And we actually had gotten to a point, my CEO, kind of half joking, actually asked the bank, you've got everything calculated to the nth degree, look up a number in this book, and then that book, and then that book, and that book, and that book. And it basically written calculated